Earlier in this chapter, we studied trigonometric equations that were identities. We now consider trigonometric equations that are conditional. That is, equations that are satisfied by some values and not others. Hi, my name is Tom Atwater. Conditional equations with trigonometric functions can often be solved by analytic methods and trigonometric identities. Let's start out with an example. Solve 2 sine x minus 1 equals 0 over the interval from 0 to 2 pi. All right, so we'll solve this analytically. So it's 2 sine x minus 1 equals 0 over the interval 0 to 2 pi. That includes 0, but not 2 pi. So to solve this problem, we're going to treat sine x as if it's one type or one variable. So I would add 1 to both sides and say 2 sine x equals 1 and sine x equals 1/2. So I'm looking for the angle whose sine is 1/2. In other words, we're going to use inverse sine function. And what that would look like is x equals sine inverse of 1/2. Now, that's one of the special angles, and it turns out that the answer, that is the angle whose sine is 1/2, is pi over 6. If we do it in radians or 30 degrees, let's stick with pi over 6. Now, we were supposed to find any solution between 0 and 2 pi. Well, sine is also positive in quadrant 2. So using pi over 6 as our reference angle, we would go pi minus pi over 6, which gives me 5 pi over 6 as my second solution. Well, we could also solve this problem by graphing the function for this and looking at that on the screen. We have y equals 2 sine x minus 1, and in the first case on the left-hand side, we see that it intersects 0 right here, and we're being told by the calculator that the decimal value is 0.52359878. And then we move to the second point where it comes to 0, and in this case, the calculator is giving us the value 2.61799939. So we can do this by both analytic and graphic methods. Let's look at the same example, only this time we're going to set it up as an inequality. Solve part A, the sine of 2x minus 1 is greater than 0, and part B, 2 sine x minus 1 is less than 0 over the interval, including 0 up to 2 pi exclusive. So let's look at the graph that we just examined, because this will help us to identify the solutions to both those inequalities. Obviously, we need to identify where the intercepts are, but we've already done that. We know it's here, and I'll go over to this graph to show the other one there. But of course, it's intersecting here as well as on this one here. And we have those two values, which I've written down here what their equivalents are. Pi over 6 is 0.52359878, and then the 5 pi over 6. Why is this helpful? Well, what we now know is we're looking for when sine of 2x minus 1 is positive. That is when it's above the x-axis. And when it's above the x-axis is between those two values. So what I can say then is that the solution to this is that x is between the pi over 6 and 5 pi over 6. And that gives me the solution to 2 sine x minus 1 is greater than 0. Well, what about for part B? Well, once again, we have to identify the intercepts, which we have, and then we have to identify for what x values the graph is below the x-axis. So we know the intercepts of pi over 6 and 5 pi over 6, so let's take a look at the graph and see how that helps us. So this time we're interested in the part of the graph that's below the x-axis. And so what we know is that it's in these two sections that I've just outlined in red. To write those out, then, we know it's going to start at 0, and it's going to go to pi over 6, and it's actually not including pi over 6. And then that we would take union with the second part, which is, again, 5 pi over 6 is not included, so that's why we use the open parenthesis. And that's going to go to 2 pi, but again, we use the parenthesis there to show that 2 pi is not included in the solution. All right. Well, when we are solving linear equations, sometimes we can factor and solve them. We can do the same thing in dealing with trigonometric functions. So let's take a look at an example. Solve sine x times tan x equals sine x over the interval from 0 to 360. So to do this problem, we'll do it analytically, and that's sine x times tangent of x is equal to sine x. All right, in this particular case, let's take and subtract sine x from both sides so that we get sine x tan x minus sine x equals 0. Because now we can factor out the sine x. And then we can say, well, if this times this equals 0, then either sine x equals 0 or tangent of x minus 1 equals 0. Then, in this case, for x to be equal to 0, then, for sine x to be equal to 0, x itself is going to be equal to 0, and x can also be equal to 180 degrees. So 0 degrees and 180 degrees for this part of the equation. What about the tangent of x minus 1 equals 0? Well, that really can be rewritten as tan x equals 1. So we're interested in when the tangent is equal to 1. The first point that happens at is x equals 45 degrees. However, where else is the tangent positive? It's in quadrant number 3. In quadrant 3, the equivalent angle would be 225 degrees. So our solution set for this particular problem is 0, 45 degrees, 180 degrees, 225 degrees. So we get 4 answers. Now let's take a look at an example where we must factor in order to solve the equation. Solve sine squared x minus 2 sine x plus 1 is equal to 0 over the interval 0 to 2 pi. So this is a quadratic equation with which we are familiar. And when we solve quadratic equations, the first method we look at is to try to factor them. So we have sine squared x minus 2 sine x plus 1 equals 0. Well, in this particular quadratic equation, we actually should recognize it as a perfect square or a binomial square. In other words, this is sine x minus 1 quantity squared. In other words, if we expand this out, we get this answer. So that just means that sine x minus 1 equals 0. So sine x equals 1. So we're looking for the angle whose sine is 1. And that means that x is equal to pi over 2. There are no other values that give us a sine equaling positive 1. So that's our solution. So let's take a look at another example of a quadratic equation in which we can't factor it, so we have to use the quadratic formula. Solve cotangent of x times the quantity cotangent of x plus 3 is equal to 1 over the interval 0 to 2 pi. So to solve this problem, first of all, I'll write it on the board, and then we will distribute out the cotangent. So we have cotangent of x times cotangent of x plus 3 equals 1. Whoops, equals 1. And that gives me cotangent squared of x plus 3 cotan of x equals 1. And now I will subtract 1 from both sides, which gives me cotangent squared of x plus 3 cotan of x minus 1 equals 0. If I try to factor that, it won't factor. What we're trying to solve for, of course, is cotangent of x, which means we have to use the quadratic formula where cotangent of x is being treated as the variable. So in other words, cotangent of x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. And that's where, of course, a is going to be equal to 1 because that's the coefficient of the x squared term. B is equal to 3, and then C is equal to negative 1. So what we have then is that cotan x is equal to negative b plus or minus the square root of b squared, which is 9, 3 squared, minus 4 times a times c, which is negative 1, all over 2 times 1. So let's simplify that. Cotan x equals negative 3 plus or minus. This becomes 9 plus 4. So it's the square root of 13 all over 2. So we need to simplify that and come up with its decimal equivalent so that we can use a calculator to help us find that answer. So I've split it up into its two values. That is, cotangent x equals negative 3 minus square root of 13 over 2. Cotangent x equals negative 3 plus the square root of 13 over 2. Now we'll turn to the calculator to get those actual numbers for cotangent of x and for cotangent of x. So let's do that. On the calculator, we want to type in negative 3 minus the square root of 13, close the parentheses, get that answer, and divide it by 2. So we have that cotangent of x has to equal negative 3.30277777. However, instead of using cotangent of x, we'll remember that cotangent of x is 1 over tangent of x. And therefore, let's take the reciprocal of this number. So I hit the reciprocal button on my calculator, hit enter, and I come up with negative 0.3027, etc. And now what I do is hit my second tan inverse button, then my second answer button, close the parentheses, and hit enter, and we get the answer negative 0.294, etc. Okay, so what that means is that the x value here is equal to negative 0.294001. Well, let's do the same thing for this side. So we'll return to the calculator and calculate negative 3 plus the square root of 13 divided by 2, and then go through the same process of the reciprocal and the inverse tan. So we have negative 3 plus the square root of 13, enter, divided by 2. So that's our cotangent of x equals that. We take its reciprocal, and now we can use the second tan inverse of that answer, and we come up with 1.276795, etc. So that means that this x value is equal to 1.276795. Okay, well now, this first solution is not in the interval that we've been asked to find. So we add pi and we add 2 pi to that number. And in that case, we'll get x. If we add pi to it, remember pi is 3.14, etc., we get 2.847591,352. When we add 2 pi to this number, so 2 pi is, 6.28, etc., etc., we end up with an answer for x which is equal to 5.989184005. Okay, well, likewise, we need to go to the second solution, which is within our range, but we still need to add pi to that to get a second solution. And so adding the pi, which is, again, 3.14, etc., we come up with a second solution that x is equal to 4.418387,679. And then my 4 solutions, if I round them off to the nearest 100th, we get x is equal to the set of numbers 1.28, comma, 2.85, comma, 4.42, and 5.99. And those are the 4 solutions to that particular problem. Well, now it's time for you to try a problem. Solve cosine squared x minus sine squared x is equal to 1 over the interval 0 to 2 pi. Pause the video while you work on this problem, and when you are finished, restart the video to check your solution. Welcome back. Let's see how you did on this problem. So we had cosine squared x minus sine squared x is equal to the value of 1. Okay. The first thing that would be good here would be to put it all into the same function. So remembering from our Pythagorean identities that cosine squared is equal to 1 minus sine squared. So 1 minus sine squared x minus sine squared x equals 1. Well, notice first of all, if I subtract 1 from both sides, that those will go to 0, and I have negative 2 sine squared x equals 0. If I divide both sides by -2, I get sine squared x equals 0. And then if I take the square root of both sides, I get sine x equals 0. So the values of x for which the angle, sine of that angle, are 0 and pi. So the solution set for x is 0, pi. Well, now let's try a problem where we will use another technique to solve the trigonometric equation. Solve tan x plus the square root of 3 equals secant x over the interval 0 to 2 pi. All right, so the problem we have is tangent of x plus the square root of 3 equals secant of x. The reason I said we're going to use a different technique here is that I want you to remember there is some relation between secant and tangent x, and this square root of 3 may or may not cause an issue. But remember, the relationship here is when they are squared. So what we're going to do is square both sides. So let's do this and square both sides. Here we have to expand the binomial, so we get tangent squared x plus 2 times the square root of 3 times tangent x plus the square root of 3 squared, which is 3, equals secant squared of x. Now I have tangent, tangent, and secant, and so I want to change them all to tangents, which would be good. And that means that we have to recall that secant squared is equal to 1 plus tangent squared. So we have then, to replace secant squared, we have tangent squared x plus 2 square roots of 3 times tan x plus 3 equals 1 plus tangent squared x. Well, what's nice is then the tangent squareds actually cancel each other out to 0. I can subtract, let's see, 3 from this side so that I have 2 square roots of 3 times tangent x equals -2. Divide both sides by 2 square roots of 3, and I get tan x equals -2 over 2 square roots of 3. The 2's cancel down to 1, and if I rationalize the denominator by multiplying top and bottom by square root of 3, I get negative square root of 3 over 3. Now, the values of x for which tangent of x equals -3, radical 3 over 3 are, of course, special angles. Tangent is negative in quadrants 2 and 4. So in quadrant 2, it's 5 pi over 6, and in quadrant 4, it's 11 pi over 6. However, I do need to check those solutions to make sure that they work in the original equation. So substitute these into the original unsquared equation. What you'll notice is if I take tangent of 5 pi over 6 plus radical 3 equals secant of 5 pi over 6, they will not be equal. So this one does not work. 11 pi over 6 does work, so that is my only solution. Well, a lot of hard work today. Good job. So in this lesson, we learned how to solve trigonometric equations that are conditions. Conditional equations with trigonometric functions can often be solved by analytic methods and trig identities. Be sure to work the examples that your teacher assigns, and we'll see you next time.